Hey, so I managed to dump and modify the firmware of the newly released Apple AirTags, effectively jailbreaking them, and in this video I will show you how I did that. Before we start hacking the AirTags though, we need to look at the hardware to understand what's inside and what's hackable. Luckily, Colin O'Flynn, famous hardware hacker and a good friend of mine, made some high-resolution pictures of the PCB and allowed me to use them in this video. This here is the front side of the AirTag, and this is where all the interesting stuff is. The big silver chip is the Apple U1, a custom chip that is responsible for the ultra-wideband functionality of the AirTag. So far, this chip was only available on recent iPhones, the Apple Watch and the HomePod, but now you have it in a $30 device, and so being able to experiment with it in a cheap way is really awesome. The second biggest chip is this one, a Nordic Semiconductor nRF52832. This is a microcontroller with integrated Bluetooth and NFC. I'm pretty familiar with it as I've seen it a lot in recent years and even published hardware tags on it in 2019. Then we also have a small 32-bit SPI flash, and as I've shown in other videos, these are in general really easy to dump. Now personally, I wasn't really interested in the AirTags at first, but on Friday morning I woke up and saw that someone sent me a dump of this SPI flash. And after taking a quick look inside, I got hooked. I looked through the flash contents, saw that it contained the RT-Kit firmware for the U1, saw some NRF code and knew that I wanted to get code execution on the device. And so I did what any hardware hacker would do. I got an appointment at the Apple Store and bought a pack of AirTags. Now what was really cool is that Colin, who by the way builds awesome hardware hacking tools for a living and also has a great YouTube channel, had already posted all the test pins and so on Twitter, and so once I had my AirTags I didn't really have to search for much. He even found 2 test pins on which the debugging interface of the nRF52 is exposed. Unfortunately, it was locked down. This means that you can erase and program the chip, but you can't dump the firmware that is on it. My goal was to change that and to try and break into the nRF52 microcontroller, as it seemed like the most interesting target. I assumed that it would run the Bluetooth stack, handle the communication with the iPhone, and probably also do a lot of other things. But how can we unlock this processor and get debugging access? Now, as said, I'm pretty familiar with the nRF52, and I also do a lot of voltage fault injection attacks. And even better, I knew that in 2020, the security researcher working under the name Limited Results published an article in which he documents how he used fault injection to re-enable the debugging features on an nRF52840. This chip is very closely related to the one found in the AirTag, and so I assumed that the same hardware attack would also work here. You can find a link to his posts and also the hardware he builds and sells in the description. And so at this point, the approach I wanted to take was clear. Let's use voltage-based fault injection to hack into the device. Now you might be wondering, what is voltage-based fault injection, or as it's more commonly called, glitching? Well, simplified, if you take the power supply to, for example, a microcontroller and you interrupt it for a very short amount of time, you can manage to change the behavior of the chip. And so, for example, you can corrupt memory reads and even skip instructions. Now, if we imagine the boot of a chip, at some point in time there might be a check that is similar to this one. The chip checks whether debugging is disabled, and if it is, it will skip enabling the debugging hardware. However, if we manage to glitch during the exact time of the check, we might be able to trick the chip into enabling the debugging hardware. And that's exactly what I did on the AirTag. Naturally, this is not super easy, but it's also not super hard. The first thing we have to figure out is, what do we want to glitch? If you look at a microcontroller, you will often see that it has a single power supply of, for example, 1.8 volts. However, in the chip, often other voltages are generated using regulators. And so, for example, the CPU core might run on a different voltage than the Bluetooth peripheral and so on. Now, when we glitch, we really want to try to only glitch, for example, the CPU core, which isn't really possible when we would try to glitch on the 1.8 volt supply. However, regulators tend to be noisy, and to compensate that, there are often external decoupling capacitors external to the chip. And these capacitors can give us direct access to the voltage of, for example, the CPU core. And so if we attach a switch to ground to that capacitor and we press down on the switch, we create a short circuit to ground that will interrupt the power to the CPU core. And if we open the switch again, power will be back. Now, obviously, with a physical switch, you won't be able to do this super precisely. And so instead of a switch, we can use an N-channel MOSFET. And instead of triggering it with our fingers, we can use a device. Now, normally you would use an FPGA or something else with very precise timings, but I thought it would be fun to try to glitch the AirTag with a $4 Raspberry Pi Pico. And so if the Pico will enable the GPIO, the power to the CPU core will get interrupted. And if the GPIO goes down again, the power will be restored. Now, how does this work on the real device? Luckily for us, the capacitor for decoupling the CPU core voltage is easily accessible on the underside of the device. You don't even have to remove the PCB from the tag, you just need to remove the backside. And even better, there's a nice test pad connected to it, which makes soldering much easier. Now a fair warning, I was impatient when I soldered my first AirTag, and I immediately ripped off the test pad and had to solder directly onto the pads of the capacitor instead. So be careful when you try this at home. Now I connected the CPU core test pad to my Raspberry Pi Pico using an N-channel MOSFET. Then, for the Pico to detect when the NRF is turned on, I also connected the power supply of the NRF to the Pico. I had to use a level shifter here, as the Pico runs at 3.3 volts and the NRF itself is running at 1.8 volts. I also connected the battery contacts of the AirTag directly to my Raspberry Pi so that I could control when the AirTag is powered on. All that's left to do now is to connect an SWD programmer to the programming pins that were found by Colin, and so after each glitch we simply try to connect to the chip using SWD, and if it succeeds we were successful with the glitching. And the nice thing is, we can try this a ton of times. In fact, we can restart the tag, glitch it, and then try to connect multiple times per second. And so we don't have to be super precise. We can basically brute force it and wait for us to get lucky. Now let's look at this on the actual hardware. This is the AirTag on which I managed to re-enable debugging and dump the firmware the first time. This is after I just had broken 2 other AirTags while trying to remove the PCB, and so you can see that I didn't have the patience anymore for a nice soldering job. I thought about doing a nicer one for the video, but I felt like showing this is more honest. Now a couple of weeks ago I started designing a Raspberry Pi Pico based hardware hacking / analysis device that includes level shifters and a MOSFET for glitching and so on, and so I used that for performing the actual attack. However, you can just as well put this together on a breadboard. If you want to support my work on it, I put a link to details in the description. And this here is the final setup I used. I'm using a J-Link as the debugger and hooked the AirTag directly up to the Pico based board. To check whether everything is working, I also hooked up an oscilloscope. The firmware on the Raspberry Pi Pico is really simple. It waits for the NRF to be powered up, then waits a configurable delay, and then it glitches the chip for a configurable pulse width. For the timing on where to glitch, I again looked at Limited Results blog post and saw that he glitches roughly where the CPU core voltage slightly dropped. And so using the oscilloscope, I roughly found that point in time and set it up. For the pulse width, I used the pulse width I used back in 2019, as I very extensively experimented with different ones back then. To control the glitcher, I wrote a simple Python script in a Jupyter notebook, which gives nicer UI output than just doing this on a terminal. As you can see, it's really simple. We loop through a delay range, then we try 2 different pulse widths, and then we use OpenOCD to check whether we can connect to the chip. So let's start it and look at the oscilloscope. We can see on the yellow line, which is the CPU core voltage, that our glitch is working. But if we zoom out, we can also see that our glitch jumps around a lot, and so it's not great. Our timing is not very precise. But remember, we only have to get lucky once. And after only a couple of minutes, the script output what I hope to see. Success. And indeed, the debugger is able to connect to the chip, and I can dump the firmware. I just managed to hack the AirTags. Yes. And the cool thing is, with the dumped firmware, I can flash other AirTags without having to glitch them. This is because the lockdown NRF52 still allows for reflashing. I tested this on a second AirTag and it works great. Next I wanted to see whether I can modify the firmware, so I changed the URL that is sent when the AirTag is NFC scanned. And what better thing to do than to try to rickroll people with an AirTag. And so when you scan my modified AirTag, you get a notification that you scanned a YouTube link and it leads you straight to a rickroll. Yes! So we've got a fully jailbroken AirTag with which we can now experiment. And I think it will be interesting to see what people build with this. Especially for research surrounding the U1 chip, it will be really interesting, and you might even be able to use the accelerometer of the AirTag as a makeshift microphone. I hope you enjoyed this video and to see you on this channel again soon. Thank you.